Hello friends, welcome to Mu Lessons. Today we will learn something about this MOSFETs. Earlier we have seen the basics of this MOSFET, so today we'll go in depth. So this is just an overview, an introduction page, just showing you the structure of MOSFET, the cross-sectional area, how MOSFET looks, and the most two important graphs which we'll study further. That is the current versus voltage graph and the current versus VDS or the drain to source voltage graph. Now the operation of a transistor. How does this operate? Now here is the gate and this is part is the insulator part. Now there has to be a channel from the source to drain, and that has to be made by using a positive or by giving a positive supply or the positive gate voltage through this. Whenever you give a positive gate voltage to this, the n-type electrons will be get attracted from this channel part, and that will create a channel, and that will make flow of electrons or the flow of current easier. And that is the basics of operation of this type of MOSFETs. So I think you are quite clear how did this happen. Now in this case you can see how the after applying positive potential a channel is created and more electrons can flow from the drain to source. This is an n-type operation, so VSG is greater than 0. It is a positive gate bias attracts electrons into the channel, and the channel now becomes more conductive. So this is a basic operation of how MOSFET works. Now talking about the physical operation of E-type MOSFET. E-type MOSFET are the most readily used and most available ones in the market, and that has many uses in electronic circuits. So first of all, we'll start with the operation with no gate voltage. With no bias applied to the gate, two back-to-back diodes exist in series between the drain and the source. Here two back-to-back diodes are existing in series condition between the drain and the source, and they prevent the current conduction from the drain to source whenever the voltage VDS is applied. So whenever you applied a potential of VDS, then this resistance or this back-to-back diode prevents the current conduction. Now how can you create a channel? Creating a channel for this current flow needs to give a positive supply to the gate potential or the gate terminal. If S and D are grounded and a positive voltage is applied to the gate, the holes are repelled. Obviously the holes will be repelled from the channel regions downwards, leaving behind the carrier depletion region. Now further increasing the VG attracts minority carriers like the electrons from the substrate into the channel region, and after getting all the electrons into the channel, it makes conduction more easy. So when sufficient amount of electrons accumulate near the surface of the substrate, under this gate an N region is created and is called the inversion layer. So in a P-type substrate you get N-type channel, and this is what we call the inversion layer, and that is made possible by applying a positive gate terminal voltage. So what happens when applying small VDS? When a small potential is applied across the gate and the source, it pushes away the holes towards the substrate and attracts electrons from the drain into the channel region, and the sufficient electrons are formulated beneath the gate and the current flows between the drain and the source. Basically the holes are pushed in the N channel MOS type to be replaced by the electrons, and these electrons are the minority carriers. So quite clear how this channel is formed. It is just by applying a positive potential which which makes repulsion with the positive parts, and the minority electrons are attracted and to create this channel. In this case, from drain to source, the ID current can flow. Now there are several questions like if the depending upon the magnitude of ID depends upon the density of electrons. So please consider with this slide, because these are written in this format. I will speak ID, VGS, these are the potential and gate source voltage. So you have to write it in subscript manner. Sorry for this mistake. Now the magnitude of this ID depends upon the density of these electrons in the channel, which in turn depends on the VGS. So for VGS is equals to VT, that is the threshold voltage, the channel is still induced and the conducted current is still negligible small. Now when this VGS is greater than this threshold voltage, the depth of the channel increases, that is ID will be proportional to VGS minus VT and is known as the excess gate voltage or the effective voltage. Now further increase in the VGS above the threshold voltage enhances the channel and hence it is called the enhancement type MOSFET. Note in this case Ig is equals to 0. There is no gate current flowing. Now what are the effects on the operation of VDS is increased. Now VDS appears as a voltage drop across this channel. When the voltage across the oxides decreases from the VGS to S to VGS minus VT at D, the channel depth will be tapered and become more tapered as VGS is increased. So you can see how it is becoming tapered as VGS is increased. Eventually when this VGS minus VDS will be equals to the threshold voltage, the channel will be at the pinch off. This line is called the pinch off and this potential is called the pinch off potential. Further increasing VDS beyond this value has no effect on the channel shape and ID saturates, or you can say the ID current remain constant and flows in saturation region. So the MOSFET enters the saturation region of the operation whenever VGS or you can say VDS is beyond the increased value. So for VDS to reach saturation is equals to VGS minus VT. And this pinch off voltage line, if you draw a vertical line parallel to the y-axis or the ID current, then you will get the pinch off voltage line, and this line divides the two regions, that is the triad region and the saturation region. This slide also shows what is the triad region, saturation region. In this part the current saturates because the channel is pinched off at the drain end and VDS no longer affects the channel. That means a constant or a consistent amount of current is flowing. Now in this case the curve bends because the channel resistance increases with VDS. Similarly, if you want to solve some examples, now design the circuit. These examples are just collected from this net, you can also find them out. Design the circuit of figure 5.24 so that the transistor operates at all the values are given, ID, VD, NMOS, K value is given, L, W. So you have to calculate or you have to design the circuit. Now since VD is given 1 volt, means operation of the saturation region, we must saturate the region and we calculate the ID half K W by L VGS minus VT whole square. So as it is operating in saturation region, we are directly using this formula. Now this equation yields two values of VGS, 1 volt and 3 volt. The first value does not make physical sense since it is lower than the VT, and in case of VGS it has to, in case of saturation region, VGS should be greater than the VT, so VGS we will take it as 3 volt. Now we note that the gate is a ground potential such the source must be of minus 3 volt and required value of RS can be determined with this formula. RS Vs minus Vss equals to RS ID, we know it previously, so RS we can get from this equation. Now to establish a DC voltage of 1 volt at the drain, we must select RD as follows. The formula for RD will be, in this case, VDD minus VD by ID, and that is what is the resistance of drain, a drain resistance RD. Similarly, there are some more examples. You can go through these examples. These are some simple examples of calculating how to design the circuit. So basic thing is, first of all you need to decide in which region is it acting and what are the constants given. Here's one more example. Analyze the circuit shown and determine the voltage of all the nodes. So you need to determine the voltage at all the nodes. So first of all, since in this case the gate current is 0, the voltage at gate is simply divided by the voltage divided rule. So Vg will be, in this case, this Vg, if you want to replace it with the Thevenin voltage, that will be 10 into 10 by 10 plus 10, that is 5 volt. Then Vgs is equals to 5 minus 60. Now by applying the equation for ID current, all the values are given in the question. You get a quadratic equation. You solve this, get the values, two values of quadratic equation. Now we'll choose which one is the correct one. So the first value results in the source voltage of 5.34, which is greater than the gate voltage and does not make any physical sense. So we'll neglect the first value and we'll take the second one. So ID is equals to 0.5 milliampere, and by substituting the values we get VGS, VS and VT. Now when you have got all these values, we need to compare it. VG minus VT is less than VD, so we got that the transistor is operating in saturation region. There are some calculations regarding the DC bias points. To operate the MOSFET as an amplifier, it must be biased at a point in the saturation region, somewhere in the saturation region. So this is the circuit diagram of DC bias point to operate the MOSFET as an amplifier. Now in this case the DC drain current can be found out by the formula. As it is operating in the saturation region, you can directly use this formula. Now we have neglected the channel length modulation, so the load line will be directly as VD is equals to VDD minus IDRD. Now to ensure that the saturation region operates, we must have VD should be greater than VGS minus VT. Next, to apply this VGS to the gate to source voltage, this VGS will be VGS plus VGS, and by substituting all the values of IDs and all, we get the whole equation of ID. So these are some applications of MOSFET as an amplifier. In the higher classes you will be dealing with them in very brief. Also we can make the small signal or the hybrid structures for these MOSFETs, so that will be small signal equivalent circuit models. These are very easy to make and very helpful in case of study of these MOSFETs and FETs. Now here are some formulas. Like the first formula is about the transconductance, GM. You can see from this figure, this is GM VT. This transconductance is given as Kn dash, that is the ratio of C, it is mu into C, K W by L VGS minus VT. It indicates that GM or the transconductance is proportional to the K W by L ratio and VGS minus VT. However, a large VGS reduces the allowable signal swing at this drain. Now for the second formula, there are some derived. These are some of the derived formulas, and you need to study them well. This is one of the important formula about transconductance, that is ID by VGS minus VT by 2, as compared to the BJT, for which GM or the transconductance is IC by VT. This transconductance value of MOSFET is much smaller than of the BJT, in light of the fact that the value of VGS minus VT by 2 are at least 0.1 volt. But in spite of the low transconductance, MOSFET have other advantages such as high input impedance, small size, ease of fabrication, low power dissipation. So these are some of the most advantages of using MOSFET. Now you can go through this example. In this problem, the MOSFET is used as an amplifier, and that has to be solved by the small signal analysis. So I will suggest you, until you don't know the small signal analysis, don't go through these problems. After you just get an idea about small signal analysis, we can't have a video on this small signal because it is a very small chapter, but I will try to give it. if possible. So further, if you go through the books and if your concepts are clear regarding this small signal analysis, then you can see some of these pictures and some of these numericals. You can go through these numericals only after understanding how this small signal analysis works. Now this biasing of MOSFET amplifiers in some different circuits, they can be used. These are some of the different biasing circuits. The first one is a single power supplier, and second one is a two power supplier. The third becomes more direct biased, and the large resistor RG forces the VG to be equal to VD in this part. So it is a self-feedback type circuit. So there are different applications, and according to the application, according to the human needs, this has been designed, and it can be further designed in future also. Nowadays these MOSFETs are used in integrated circuit. This is shown as a current mirror circuit. This particular MOSFET acts as a current mirror circuit. The two reasons that make the biasing circuit for discrete amplifiers not practical for IC amplifiers is extensive use of resistors. So this is very important point to remember. The basic two reasons that make these biasing circuits for discrete amplifiers not for practical IC amplifiers, because in these cases we are using extensive use of resistors and capacitively coupled input and output system, but that is very not required in case of IC amplifiers. These are only made for this discrete amplifiers. Now there are certain formulas of the current mirror circuit. ID1, that is the current flowing in the first MOSFET, is half K n dash W by L VGS minus VT whole square, and this ID1 is equals to the I reference point, that is VDD minus VGS by R. Similarly, I output will be ID2, and if you calculate the ratio, then that will be the ratio of W by L2 and W by L1. So the two significance of current source, constant current source, is a simple relationship of I output and I reference by the ratio aspect of the geometry. Whenever I0 is equals to the I reference point, it is called the current mirror circuit. These current mirrors are essential building blocks in design of IC amplifiers. So there are many more applications of MOSFET. These are some of the applications of common drain amplifier, source follower amplifier, and this needs an extensive study of analysis of small signal analysis. So only after you are quite clear about the small signal analysis, you can work them out well. Now one of the most important use of this MOSFET is the complementary MOSFET. Complementary MOSFET consists of two types, that is NMOS and PMOS, separated by semiconductor silicon dioxide. Now the combination of these two complementary type makes this CMOS. Now these CMOSs are used to make the NOT gate or the inverter. You can make in this format. Other gates can also be made. So this is the diagram of CMOS. Now in this case, the positive gate turns on and MMOS on. So we get the output. The positive gate in this part, positive gate turns the NMOS on and V0 equals to 0. Now the negative, by applying negative or 0, negative gate turns the PMOS on and we get the output. So in this way, by applying 1 you get 0, and by applying 0 you get 1. This is nothing but just an inverter or a NOT gate. This CMOS can also be used to create NOT gate. We can create other gates like NAND gate, XOR gates, and it has very much applications. So this is a table of NAND gates. So you can make many more types of gates using this CMOS, and they are widely used nowadays. So this was all about the MOSFET part, how these MOSFET are made, and the wide variety applications of MOSFET in our practical uses. So we'll come up with some more videos next time. Till then, all the best. Thank you.